Many times, propagating rays through an optical system don't give an accurate picture of what's actually happening within the optical system. This is because of diffraction and other small-scale effects that can occur as the light propagates through the optical system, including some polarization effects. Within ASAP, there are additional techniques beyond simple ray tracing to analyze what happens to the energy as it propagates through your optical system. One particular technique is called Gaussian-beam decomposition. With Gaussian-beam decomposition, we use a ray-like model to propagate wavefronts through our optical system, and what we do is define our wavefront as a collection of Gaussian beamlets, and we propagate those beamlets through the optical systems. As the beamlets become aberrated, it introduces the aberration to the wavefront as a whole. Let's look at a couple of examples. First thing we might want to look at is the point spread function as our wavefront propagates through our optical system. In this particular case, we're going to define a 23 by 23 set of Gaussian beamlets to propagate through the system, and then we'll look at the results at the output. So here's my beamlet distribution. And here's my optical system. You'll notice that there's some apertures that are clipping off some rays that would introduce diffraction effects. And let's change the scale on this so it looks more square, which is what the actual output would be. What we see here is the point spread function for this particular optical system. And we can move our crosshairs to any location, and you'll see the graphs on the right and below update to indicate the data about the current position of the cursor, including the value as well as the positional information. Let's look at a bit more complicated case. We can see the effects of the aperture diffraction here, but this is a nice circular aperture in a rotationally symmetric optical system. We can also have other shaped apertures, including, for instance, a triangular aperture. And what we want to do is see what the effect of this triangular aperture is as the light goes through our optical system. And again, we're going to see lots of clipping and diffraction at the boundaries of this aperture. So again, let's look at our lens first. And this is the location of our triangular aperture. And here's the diffracted output, or the point spread function due to the diffraction. This is exactly what we would expect from a triangle, because we would expect to see spikes perpendicular to each of the edges, and with the 3 edges of the triangle, we indeed see the 6 spikes, exactly as would be predicted by diffraction theory.